The topic for this video is electron configuration. So now we're going to take the quantum mechanical model we talked about in the last video and talk about how the electrons fill into this quantum mechanical model. So this is going to be focused on deriving the ground state electron configurations of the atoms, which again goes back to this connecting the electronic structure of an atom to its periodic properties. Where we left off last time was this image of the orbital geometries. And I told you, the actual shapes of them aren't as important as the names and the number of them there are. So to repeat last time, there are 4 different types of orbitals. The S, the P, the D, and then the F, which are these last 2 rows. Each of those types has an increasing number of orbitals within it, what we call sublevels. A sublevel are 2 orbitals that have the same energy. So there would be 3 sublevels in the p orbitals. There are 5 sublevels in the d orbitals. There are 7 sublevels in the f orbitals. There is also the obligatory 1 sublevel in the s orbital. Electrons fill into these orbitals in a very specific and predictable pattern. All right. So I'm going to show you an image of what this pattern looks like. So this would be what we call an orbital diagram. So it's laying out the orbitals and the sublevels in a way such that you can make some judgments about the energy of the electrons. So on our left side here is the arrow pointing up. This is increasing energy in the system, right? So the higher the level is on the left side, the higher the energy level of the electrons occupying that orbital. Each of these lines represents a distinct orbital. Now underneath you see the labeling. There's a number and a letter. The number is what's called the primary quantum number. You could roughly compare it to Bohr's original ideas of what the atom shape looked like, or the orbit shape looked like, right? So he had level 1, level 2, level 3. That's kind of where these are at, right? So first energy level, second energy level, third energy level. So you can see these jumps between 1 to 2, 2 to 3. Now 3 to 4 it starts getting weird, and when you start entering into the d orbitals and stuff, it gets bizarre, and we'll talk about that. So that's just what this is called, the quantum number, the principal quantum number, the primary quantum number. That has to be there. That tells you which of the energy levels you're in. The letter designates the orbital shape. So S, P, D, and then if we went farther up, you get to F. Note, the sublevels are denoted. So there's 1 sublevel for each of the S's. There's 3 sublevels for each of the P's. And then there's 5 sublevels for the D. Now you'll note it's pretty predictable. 1S, 2S, 2P, 3S, 3P. But then it gets a little weird right here, right? It goes from 3p to 4s to 3d to 4p. These d orbitals, these are what represent the transition metals, and we're going to talk about those in a little bit, probably in the next talk. It gets really bizarre once you get into where you're doing the transition metals. All you need to remember is you go from 3p to 4s to 3d to 4p. Right now, I'm going to show you a trick on how you can remember this using the periodic table in a later talk. Okay, whenever we're talking about putting together one of these orbital diagrams, which is what I just showed you, we're essentially putting together the basis by which we can write an electron configuration. And I'll show you the difference between the 2 of them in a minute. To do this, we have to follow a very simple procedure. All right? So first, all ground state atoms have the same number of electrons as protons. So the atomic number, which is the number on the periodic table, is both the number of protons and the number of electrons in an electrically neutral atom. That's what ground state means. All right? And it makes sense. Each electron's got negative charge, each proton's got a positive charge. So if I want to have a charge of 0, which would be neutral, I would need 1 of each, right? So same number of electrons as you have protons. So you look at the atomic number, you say, oh, the atomic number is 5, I have 5 electrons. Next thing you're going to do what's called off-bow. Off-bow means you start filling in at the lowest available energy first. All right, so you start at the bottom, work your way up. That's all off-bow means. Second, Pauli exclusion principle. Each orbital, so each of the little lines on our diagram, each orbital can only hold a maximum of 2 electrons. Now note it says with opposing spin. There is a property of electrons called electron spin, and it is a quantum mechanical property, and it's important when you're determining magnetism and stuff like that. You're not going to need to worry about it. I'm going to show you how we're going to denote opposing spin. It's in there because it's part of the definition, but it's beyond the scope of where we're going to be. Okay? The big thing you need to remember is each of the orbitals can only have 2 electrons max. All right? That's Pauli exclusion principle. The last principle is what's called Hund's rule. Now, Hund's rule is probably the hardest one to make sense when you're just reading it, but it's really easy when you're doing the diagram. I'm going to show you how to do a diagram in a second. Hund's rule says electrons are distributed in orbitals of the same energy as to maximize the number of unpaired electrons. What that simply means is if you have an incident where you have more than one sublevel, so that's p, d, or f orbitals, you've got to fill each of the orbitals, each of the sublevels, in that principal quantum number with 1 electron before you can fill any of them with 2. All right? That's all Hund's rule means. So let's look how this plays out in an actual example. So we're going to work with sodium. Now, if we look at sodium, we know it has 11 electrons, right? So hydrogen's 1, lithium's 3, and then sodium will be 11, right? So 11 total electrons. So I'm going to start at the bottom. So as you see down here, 1s, that's where I start. The little arrow denotes an electron. Now, that's off-bow. Pauli exclusion principle. I can fit a maximum of 2 electrons in there, and they have to be opposing spin. The way we denote opposing spin is by putting opposing arrows. Those represent the up and down spin of the electrons. All right? So that's Pauli exclusion principle. Keep following off-bow and Pauli exclusion principle. Now I've filled in 4 of the electrons. Now we need to get into the last one, Hund's rule. Hund's rule says that the way the P's are going to fill in is they're going to fill in with each of the sublevels getting 1 and then filling in the second. All right? So this takes us to 10 electrons. My 11th and final electron goes in the s position, 3s position. So this would be an orbital diagram for the 11 electrons of sodium. Now there's a number of practice problems on the website on how to do this. This is an orbital diagram, but we want to get to electron configuration. The problem with an orbital diagram, it takes a lot of space. And quite frankly, once you understand what it's representing, most of this is unnecessary. Most of this drawing and, pretty arrows and stuff really doesn't convey information that's necessary because you know it already, right? If you understand the rules of how to fill in an electron configuration, you know the first number is always going to be the lowest energy level because that's off-bow. You know that each sublevel is only going to have a maximum of 2 electrons. That's Pauli's exclusion principle. And if you know there's 2 of them, you know they're opposing. And 3, you know if you've got an incompletely filled set of 3 sublevels that it's going to fill in so that you have the maximum number of unpaired. So we can actually take most of this and jettison it to write a kind of shorthand for this. And the shorthand is what we call an electron configuration. So the electron configuration for this is written as such: 1s2, 2s2, 2p6, 3s1. Note, principal quantum number, orbital structure, and then how many electrons total are in that orbital structure. So I have in the 1s, 2 electrons. In the 2s, 2 electrons. In the 2p, I have 6 electrons, and in the 3s, I have 1 electron. Off-bow tells us this is the lowest energy one. Pauli says that there must be 3 sublevels in this, because you can only have 2 per sublevel. Pauli also tells us these all have to be paired, right? And we know this is an unpaired one because there's a maximum of 2. So everything fits in this way, right? It's just the shorthand for the bigger picture. Granted, on the exam, I'm going to ask you to do both. I'm going to have a problem where you're going to have to do an orbital diagram and you're going to have to do an electron configuration. But even this can get extremely tedious over time. And the fact of the matter is, most of these electrons aren't actually usable for chemistry. It is only the outermost electrons, the last principal quantum number, right, that's actually usable for chemistry. Because everything before that is locked in a stable system. We call this a valence abbreviation. The first 10 electrons here look like the electron configuration of the noble gas neon, which has the atomic number 10, the one directly preceding sodium. Those electrons are not chemically active. They're what we call core electrons. The only electron that's chemically active is the 3s electron. So we denote it this way. We convert these three into the noble gas that they were, follow it by what are called the valence electrons, the ones that are actually going to do the chemistry. So this is how we put together an orbital diagram, electron configuration, and a valence abbreviation of that electron configuration. You should be capable of doing this entire type of problem before we get to the next exam.